So, yeah, recording started. So, welcome to this evening's presentation. Firstly, I would like to acknowledge country that we are all meeting on today, and we are meeting on different lands across Australia. So I would like to acknowledge the traditional custodians of all the lands on which we are gathered today, the lands we work and live on, and I recognise the continuing connection of Aboriginal and Torres Strait Islanders to their land. Also their waters, the biodiversity, the culture, and I pay my respects to elders past, present, and emerging in all those lands that we are meeting on today. So this is the Drought Resilience Leaders Program, and it is part of the ARLF, which is the Australian Rural Leadership Foundation, and it's being brought to you in partnership with a number of organisations, and this includes the National Farmers Federation, the Foundation for Rural and Regional Renewal, Rural Economics Centre of Excellence, the Australian Resilience Centre, and University of Southern Queensland. And we truly value the working relationships that we have with these organisations and the work that they do across rural and regional Australia. And this Drought Resilience Leaders Development Program is funded by the Australian Government's Future Drought Fund. So before we kick off, just a few housekeeping. So please stay on mute. Unless you're participating in the Q&A at the end of the session. So having yourself on mute will just enable us to hear our presenter more clearly. And then there'll be lots of time for the questions and discussions at the end of the presentation. We would love to know who you are and where you're zooming in from this evening. So feel free to put that in the chat box. I'm in far western New South Wales near Broken Hill on beautiful Williakali country. The recording of this session will also be available on Mighty Networks tomorrow. So if you have to jump out early this evening, we totally understand. You can access the recording later and watch it before our next session begins. So I would now like to introduce Dr. Ian Smith. So it's a great pleasure to welcome Ian here this evening. Dr. Smith is a highly experienced climate scientist and lecturer who spent many years working in CSIRO and the Bureau of Meteorology. He has published extensively in the scientific literature on climate variability, climate change, climate prediction, and long-term climate change projections. He now runs a consultancy and he works part-time for the University of Southern Queensland's Centre for Applied Climate Sciences. So Ian, welcome to the floor. We look forward to your presentation.
Thanks very much, Anika, and thank you very much for tuning into this talk. I'm located in Melbourne at the moment. We're all located in various locations around the country, it seems, but I would like to acknowledge what's going on up in Queensland and New South Wales, and hopefully our audience is not too adversely affected by events up there in terms of their friends and family. As Anika says, this is a talk about climate. We're talking about past, present, and future climate, how it affects both the globe, the country, New South Wales, and with a bit of an emphasis on the northwest slopes. And as Anika says, I used to work for CSIRO in the Bureau of Meteorology. I retired, but I'm now a part-time research associate with the University of Southern Queensland. And I'm working with a bunch of people, Scott Power, Kate Reardon-Smith, Shamila, Sir, and Nina, who are have provided a lot of the material that I'll be presenting today. Nina Usher, that is. I just lost the screen there for a moment. And there's a lot of material to get through because climate change and climate variability is a huge topic. But what I'm going to do is to restrict myself purely to what is publicly available in terms of information about climate change and climate variability as available in the public domain. And what I'm referring to here is the wealth of information that is available, published by organisations such as the Intergovernmental Panel on Climate Change, the Bureau of Meteorology on their website, and the sites and publications put out by both national and state government authorities. So what I'll be doing is to try and cover the material in an efficient manner as I can. I'll be talking about the what and how of climate change, dealing specifically with what we can say about things such as rainfall and temperature, but I won't be talking so much about the impacts of changes to these variables. And I think the time and place for discussing impacts and the issues of the adaptation to impacts of climate change will come in another session down the track where I think Anika will be sharing discussion groups and talking more about how to deal with the possible impacts of climate change going forward. And as Anika says, hopefully we've got time for questions. If not during this session, then I'm happy to get back to people with answers that can't be dealt with in tonight's session. So just contact Anika, and I'm happy to contact people via email, etc. So just looking at the talk overall, this is the structure. You can see here that it's divided into really two halves. One is the past or the recent past, and that deals with things such as climate variability, El Nino, La Nina, how has climate change, what caused the changes, and then in the second half, the future and what is projected for the decades ahead, both globally, for Australia, New South Wales, and for the Northwest Slopes region. And to begin with, I'm sure you may be familiar with some of this material, but it doesn't hurt to revisit it and maybe get another perspective on the material dealing with Australia's variable climate. And it's highly variable in terms of the rainfall. And here we've got a series of maps showing the annual rainfall anomalies across all of Australia for every year between 1970 from the top left-hand corner right down to 2021, the bottom of the screen. And you can see a huge variation from year to year in terms of where it's wet and dry. There are large-scale patterns. There are hidden in all this data. There are ups and downs which we can detect in terms of the El Nino, La Nina phenomenon. And potentially there's also some trends there, and it's very hard to see by just looking at all these maps on the screen like this. But I will draw your attention just to two of the maps. So if you look at the bottom right-hand corner of the screen, you'll see the map for 2019, covered mainly in red, which indicates that most of Australia was dry in that year. And in fact, that was both the driest year on record combined with being the warmest year on record. So it's a highly significant year, and that particular map is very important in terms of the climate science and climate change. And if you direct your eyes to the left of the screen to 2010, it's on the same row, but to the left of that 2019, you'll see another map where it's much of eastern and central Australia is covered in blue. And that corresponds to a very wet year. And this 2010 corresponds to what's called a La Nina event. 2019 corresponds to the opposite event, the El Nino event, which I'm sure you're familiar with. El Nino as being associated with droughts, La Nina being associated with above average rainfall. And even the last map in the series, 2021, you can see that southeastern Australia, or much of eastern Australia, is relatively wet. That was last year was a La Nina year, and it looks like it's continuing on into this year. So we may be experiencing a double La Nina at the moment. If we go and focus a bit on the rainfall record within the Northern Slopes region, you might be aware of the rainfall site known as Curlewis. And what I'm plotting here in the time series is a graph of annual rainfall for every year, starting back in 1900 right through to 2020. And the first thing you might notice is that there are some years with no data. Well, that's not unusual when looking at raw rainfall records. Sometimes there's no data due to technical issues or a whole range of issues. But we do have here over 100 years of data. And if you just ignore the missing years, you can see straight away that the long-term average, as indicated by that blue line, is about 600 millimetres of rain in a year. And that might be typical for our audience in terms of how different, in terms of how far away out they are from this particular rainfall site, Curlewis. But what's probably common to much of the Northwest Slopes is that in 1950, they would have experienced higher than average rainfall, a very wet year. And in 1982, they would have experienced below average rainfall. And this is indicated on this time series by the two triangles. The blue triangle indicating 1950, a La Nina year, where the average rainfall was almost twice the long-term average. And 1982, the drought year, where rainfall, not quite half the long-term average, but significantly below average. So it's possible to look at other years and identify El Nino years, La Nina years, and above and below average rainfall associated with those events. And the other thing we look for is evidence of any trends in the data. And to be honest, if you, even ignoring the missing data, if you were to look at the long-term trend in the rainfall for Curlewis at least, it's very hard to see if the rainfall there is going up or down. So bear that in mind as we talk about climate change and projections for the future. Now, I mentioned El Nino. Again, a lot of you will be familiar with El Nino, or ENSO as we refer to it. The El Nino Southern Oscillation, the acronym is ENSO. EN stands for El Nino. And that the EN really represents the fact that the phenomenon is associated with changes in the temperatures of the Pacific Ocean, or the equatorial Pacific Ocean. And the SO in the acronym stands for the Southern Oscillation. And that refers to the atmospheric component of the phenomenon, because during ENSO events, we witness what's called a coupled phenomenon, in whereby the oceans adopt a certain, become set in a certain phase, and so does the atmosphere. And we can measure both in terms of the gradient in temperatures across the equatorial Pacific, and in terms of the atmosphere, we measure that in terms of the pressures at Tahiti and Darwin, which gives rise to what's called the Southern Oscillation Index. And most of the time we're in a neutral phase in terms of ENSO, but ENSO events tend to reoccur roughly every 4 to 5 years. It's not exact, it's highly irregular, but on average it's every 4 to 5 years, which means that in the long term, typically a quarter of the time we're in one of the phases, either a wet or dry phase. And the rest of the time we're in a neutral phase where, in particular, we don't have a great deal of, we don't have the opportunity to produce really meaningful outlooks. We're more subject to the vagaries of the variable climate in the neutral phases. Now, again, I don't want to get too technical, but I think it's useful to just have a look at what I've referred to as the coupled phenomenon, and just to describe it in a little bit more detail. We have two figures here, and the one on the left corresponds to the La Nina phase of ENSO. And during the La Nina phase, what tends to happen is that temperatures in the Western Pacific and to the north of Australia tend to be warmer than average. And the warmer than average sea surface temperatures promotes enhanced convection, increased rainfall, which we experience, especially across northern and eastern Australia, and also lower than normal pressures. And if you look across to the eastern Pacific, the reverse occurs. The temperatures there are cooler than normal. Convection tends to be suppressed. They get fewer or less rainfall, and the pressures there tend to be above average. And then the second figure on the right-hand side of this slide represents almost the opposite situation, the El Nino phase, whereby to the north of Australia, we have cooler than average temperatures. These act to suppress convection to some extent and reduce the chances of rainfall events over northern and eastern Australia. But on the other side of the Pacific, adjacent to South America, the temperatures there are warmer than average, and that's where you tend to see greater convection and more rainfall. So it's a shift from one side of the Pacific to the other. And as I say, it's not regular, it's somewhat irregular. And the difficulty is predicting it a long time ahead. But once we see it developing, then our prediction capabilities come into play. And once we see the whole system switching into one phase or the other, then we've got a handle on what to expect over the coming months, because once it sets in, it tends to last for a year or so before eventually decaying. So the impacts of these phases, and the two maps here provide an indication of what you might expect once we're in one phase or another. And the left-hand map, without going into too many details, it's green and blue and dark blue. Those colours indicate where during a La Nina phase, during winter and spring, this is where you would expect rainfall to be above average. And on the right-hand side, during El Nino phase, the yellow, red and dark red indicate where you can expect winter spring rainfall to be below average. And if you can focus, or you can see on these maps, the northwest slopes region, you'll be aware that it falls well within the blue and the red parts of the maps on both sides. And that means that ENSO does have a significant effect on rainfall in your area. And these these maps are based on observations, and I'll just point out that the one on the left is based on 13 La Nina years since the turn of the century, or the turn of the 20th century. And the one on the right is based on 14 El Nino years over that period. And the colours represent deciles, which I won't describe, but I'll assume that you understand what decile maps are. Now, what does the current situation look like? Well, we can see the pattern of sea surface temperature anomalies that exist as we speak. And this is a global map of sea surface temperature anomalies, which was produced on the 21st of February, just over a week ago. And as you can see, the red and yellow and orange areas representing the warmer than average temperatures are clustered around the north of Australia and in the Western Pacific, particularly the equatorial regions where ENSO is, where the ENSO action takes place. And again, we see the opposite conditions in the Eastern Pacific, where the blue colours indicate cooler than average temperatures adjacent to South America. So we can see, right, it's quite obvious that we're in a La Nina phase, and recent events are consistent with being in a La Nina phase for quite a period now. These anomalies have been like this for months and months and months. And that, as I mentioned, they don't go away very quickly, so they will probably be there for another few months at least, in which case the signal, or the ENSO signal that we've been experienced to date, there's a high chance that we'll continue to see those impacts over the next few months. And this forms the basis for the rainfall outlooks which the Bureau produces. And in this case, I've got a map with colours on it. And again, the colours represent the chances of receiving above median rainfall for the March to May period of this year. And this was issued just over a week ago. And as I say, the sea surface temperature patterns, the phase of ENSO lies behind this particular map. And as we've seen with the impacts map, this is consistent with what we've seen in the past, that the chances of getting above average rainfall are enhanced over much of Australia for this particular period, March to May, particularly along the eastern coast. And again, what I've tried to do here is draw an arrow pointing to the Northwest Slopes region, which is represented here by the green colouring. And the green colouring suggests, in terms of numbers, there's a 60 to 70% chance of getting above median rainfall over the next 3 months. And if people are unclear how to interpret that, then please get back to me. But I should stress that these aren't what we call categorical predictions. They're unlike the weather forecast. The weather forecasts are definitive predictions about what will happen tomorrow or the next few days. It will rain, for example, or it will be cold, or it will be windy. These are probabilistic predictions or outlooks. And so when the Bureau says there's a 60 to 70% chance of receiving above median rainfall, all that represents is a shift in the odds, because the corollary to that outlook is that there's a 30 to 40% chance of receiving below median rainfall. So that's something that people need to be aware of. It's not a categorical prediction, and it should never be interpreted as such. It's just an indication that the odds have shifted one way or the other. Now, how good are these outlooks? And I only discovered this recently, and I thought I'd have a look back at the Bureau and the outlooks were saying back almost before spring of last year. So I think this would have been early September that the Bureau would have been putting out this sort of information, and it's titled Regional Hazards for Spring and Early Summer. And you can see that the map of Australia is coloured in greens and blues, again representing the shift in the probabilities towards above average rainfall for spring and early summer for much of Eastern Australia. But they've also looked at some of the impacts that tend to be associated with this phase of ENSO. And you can see here the little boxes there refer to tropical cyclones. They were suggesting way back then that there might have been an early start to the tropical cyclone season. For Queensland, they're talking about flash flooding due to storms, severe storms, heavy rainfall. There's mentions there of high fire danger for parts of northeast New South Wales, mainly because at that stage there were high fuel loads and it had been relatively dry up to then. So there was a risk there was a fire risk back then. Working down further south, flooding in parts of New South Wales, Victoria, and even Tasmania, across to northwest Victoria, severe storms, right across to WA, Western Australia, fire danger again due to recent dry conditions and high temperatures. And that one turned out to be almost on the money because they did experience early season bushfires. But I'd just like to say that given this was put out in before the start of the spring, early summer season, in the words of our Prime Minister, how good is that? I'm mightily impressed by the information content there. Not all of it is 100% correct, but certainly there's a lot of useful information there for people interested in planning for the season ahead. So just to summarise that part of the talk, that rainfall, as we all know, is extremely variable in Australia. Some of this variability, not all, is related to variability in ocean temperatures, the Pacific and Indian Oceans. And I haven't talked about the Indian Ocean. I don't think I have enough time to discuss the Indian Ocean dipole. It's not that, it's important, but not that important for the northwest slopes region. And the fact that we can monitor and detect the development of ENSO phases means that seasonal rainfall outlooks can be prepared on a regular basis. Regularly, I'm meaning, again, roughly every 4 to 5 years. In the neutral phases, outlooks are a little bit less certain. So moving on through the talk, how has climate changed? So in moving on to this topic, we're leaving behind variability on the timescales of months and seasons to decades and longer. And we're looking at what has happened to Australian climate over the past typically 100 or 50 to 100 years. And when we look at what's happened in the past, a common time series that is often shown is this time series of global, it's not Australia, it's the global average temperature over both land and oceans from 1880 right through to 2020. So it's quite a long period there. And this time series is based on the careful analysis of available thermometer records readings taken over stations all across the globe, temperature readings taken from ships that have been traversing the oceans over that period, and aided by satellite, more recently satellite-based observations. And a lot of work goes into trying to reconstruct the temperature record. So it's fairly well recognised that this is the best available estimate of what's been going on over that period of time. And the things that we see when we look at that time series include ups and downs. Some of these ups and downs reflect ENSO events, because ENSO doesn't affect just Australia. ENSO affects rainfall and temperatures over wide regions of the globe, and that signal can be detected in this time series. And the other thing we can see is an upward trend in temperatures, particularly after 1960. And the increase in global average temperatures since then, at least, is of the order of about 1 degree. And if we went back further, it's probably much more than that if we look back to, say, the early 1900s. And as I say, this is based on all available measurements from thermometers and careful analyses by climate scientists over decades. And the Intergovernmental Panel on Climate Change refers to this as scientific evidence for warming of the climate system is unequivocal. And that's worth stating because some people dispute the fact that the globe has warmed. But even if they do dispute, even if you do have doubts about whether this is a true and accurate representation of a warming world, you only need to look at all the changes that have taken place in the environment. And the things that have been associated with a warming world, which are all consistent with global warming, there are many, and I'll just indicate some of them that are shown on this particular diagram. One of the compelling lines of evidence of a warming world is the retreat of glaciers all across the world, from New Zealand to New Guinea to the United States, Asia, everywhere around the world, glaciers have been retreating. The other thing that people have noticed is that sea ice has been decreasing, particularly around Antarctica at the moment. The annual march of sea ice, which reaches a maximum in winter and a minimum in summer, right now it is at record lows. The other thing we note is that sea level has been increasing, and that's very well monitored and measured. And the rise in sea level is consistent with the fact that the oceans are warming up very slowly. And once they start warming, they tend to expand. And part of the sea level rise we see is due to the warming of the oceans. And there are various other impacts of a warming world, which I won't go into. Things people have noticed about tree lines shifting poleward and upward, springtime coming earlier, species migrating. And one which I'm particularly interested in is the fact that wine growers have decided en masse to set up shop, or many of them have decided to set up operations in Tasmania because being a cool climate region, global warming will make it more and more attractive for growing grapes compared to, say, places on the mainland where warming and heating or hot temperatures aren't conducive to growing good grapes. So that's another indicator of changes that people have noticed. And if we look at Australia, we've got a time series of annual average temperatures over the long term from 1910 to 2020. And again, you can see the temperatures go up and down from year to year. We see ups and downs again. Some of them are associated with ENSO events. And we also see an upward trend. And if we looked at, say, 1960 onwards, we're seeing on average Australian temperatures increasing by about 1.5 degrees Celsius. And you can see at the end of that time series that the red bar corresponds to the 2019 year, that remarkable year when Australia had both the driest and hottest year on record. And what's interesting is, as you can see, the record tends to be consistently broken as you move forward, say from 1970. The maximum in, say, about 1970 or just before 1980 was broken in, about 1995. And then it was broken 5 years later, and then it was broken 5 years later, roughly, and then broken again in 1990. So this is very compelling evidence that Australia, like the globe, is warming and at a seemingly inexorable rate. What about the pattern of warming? Well, again, we can plot the trends in temperatures across Australia. In this case, from 1970 to 2020, a 50-year period. And you can see where the warming has taken place. The red areas indicate where it's warmed the most. And again, the Northwest Slopes region lies very close to where the maximum warming has been apparent over Australia. That red region near the Northwest Slopes corresponds to a rate of increase of about 0.3 degrees per decade, or in other words, over the 50 years since 1970, an increase of the order of 1.5 degrees. And the general pattern you see there is that the warming tends to be more apparent over inland areas compared to coastal regions. And the only area on the graph where there hasn't been any warming would be that little spot up in the Northern Territory. And that's explainable by the fact that over that same period, things have been getting wetter up there, and the wetter conditions in that part of the world go hand in hand with increased cloud cover, less sunshine, and cooler conditions. So that's easily explainable. If it hadn't been getting wetter, we'd imagine the pattern would have been even more uniform. And what about the rainfall trends? Well, again, what we're showing here is a period from 1970 to 1920, where the trends in rainfall have been calculated and plotted on a map. And the green areas indicate where it's been getting wetter. The paler brown and darker brown regions indicate where it's been getting drier over that 50-year period. Not all these trends are significant. It should be these sorts of maps that need to be treated with a little bit of caution, because you can see a colour indicating a downward trend, but statistically speaking, some of these trends aren't significant. In other words, they're not robust. They could change with another year's data, for example. But the ones that are statistically significant and are very unusual are the increases in Western Australia and Northern Australia. The decreases in Southwest WA, now they don't look very important on this map, but they have been quite significant and have had major impacts for Perth and the surrounding areas down there. For all the other regions, I would like to say that there's a definite long-term trend towards drying. More work needs to be done in analysing the data, or the more recent data. For example, if we look at that rainfall record for Lewis, which I showed earlier, and it's reproduced here on this slide, the line indicates where Lewis is approximately. Forgive me if I've got that wrong. I might have mentioned the fact that when you looked at the Lewis rainfall record, it's very hard to spot a long-term trend, either up or down. But at least from 1970 to 2020, the map that's there shows that the rainfall may have gone down slightly, something to the tune of maybe 10 to 20 millimetres per decade since 1970. But again, I wouldn't read too much into that at this stage, because rainfall is so highly variable that some of these trends can't be regarded as too significant. So what does the government say about climate change in New South Wales? Again, I've more or less covered these points, but this is what you can find officially. All of New South Wales has warmed. Inland areas have experienced more warming than coastal areas. Annual average rainfall over New South Wales, it shows large decadal variations, but no long-term trend. And the interesting impact of some of these changes is that the number of days with dangerous weather conditions for bushfires has increased across the region. So the next question, given that we've observed those changes in temperature and rainfall, what has caused the changes? And in attempting to answer that question, what climate scientists do is resort to climate modelling. And climate modelling, very briefly, a climate model is almost the same as a weather forecast model, which is used to predict the weather on timescales of a day or days or up to a week ahead in time. It solves the equations which describe the evolution of winds and temperatures and pressures, etc. Does that all across the globe, right up through layers in the atmosphere. But for climate modelling, they don't just run the models for a 1 week or 10-day period. They run them for long, extended periods of time, decades and centuries, and they look at the results and the statistics of the results that the models put out. And there are three things that are input to the models and which determine the results for things like global average temperature. And there are three main drivers I'll mention. The first one is obviously increasing concentrations of greenhouse gases. The second driver that goes into these modelling experiments is the history of volcanic eruptions. And these determine how much gunk is spewed up into the upper atmosphere. And the gunk is an expression for atmospheric aerosols, which tend to reflect sunlight back. So if you have too many aerosols or too much gunk in the atmosphere from volcanoes, it's possible that has a cooling effect on the global temperatures, which has been observed. And the third driver that we put into these experiments is variations in the output of the sun, which we know have occurred. The sun's output is relatively constant, but it does go up and down by a little bit, particularly with the changing sunspot numbers. So the climate experiments have a look at the effect of these three drivers. And the important one here is the carbon dioxide concentration, which we know pretty well over time. Here are measurements taken at the Mauna Loa Observatory in Hawaii, and shows you that CO2 concentrations have been going up from about 300 in 1960 to over 400 in 2020. That's a rather large and rapid increase of 30% in 60 years. We also know the variations in the output of the sun over the past 100 years, and we also know we've got a pretty good handle on the impacts of the volcanic eruptions over the past 100 years. So bearing that in mind, when we do climate experiments, this is what the climate scientists find. And this is a time series of, again, global annual average temperature. And the observed warming is given by the black line, if you can make that out. So with the black line shows you the ups and downs up until 1950, then increasing dramatically right up into 2020. So that's observed. And the question is, what do the climate models say when we put those forcings in? And we get two sets of results. And one set of results is indicated by the green part of the graph. And the other set of results is indicated by the pale orange, pale brown part of the graph. Now, the first set of results is what you get when you run these models and you only put in changes in the output from the sun, or the strength of the sun, and changes in atmospheric aerosols associated with volcanic eruptions. Again, we know these going back over 100 years. If we prescribe those drivers to the climate model as inputs, the results of the climate model for global annual temperatures, they go up and down, they reflect the effects of the aerosols, they reflect the effects of the changes in the sun, but they don't produce the rapid warming that you see at the end of the time series. However, the second set of results is what you get if you put in the increasing carbon dioxide concentrations, which we know. If we put them in, you can see that the set of results differs from the first set of results by reproducing pretty much the observed increase in temperatures after 1950. So this is an important graph published by the IPCC, and it describes what's called an attribution study. That is an attempt to describe or understand why changes have happened in the past. And in this case, the take-home message is that from all we know about what affects global annual average temperatures, the only factor that can explain the recent increase in temperatures is increasing carbon dioxide. All the other known factors aren't large enough to help explain that. So, having performed an attribution experiment and investigated what has caused changes in the past, the next thing is what's going to happen in the future. And again, what we do is resort to climate model experiments. Given that we've got a good handle on simulating global annual average temperatures, we use those same models, and we don't just stop them at the present. We don't just run them for 100 years from, say, or 150 years from 1850 to the present. We keep running them forward in time, and we go out to the end of this century. And whereas when we're looking at the past, we know from the historical record, what the carbon dioxide concentrations were. We know what the volcanic eruptions were, and we know what the solar variations were. When we head forward, we don't know what those things are, but we can at least do the following. We can keep the solar, the strength of the sun, or the input due to solar radiation constant, because that's not going to have a huge effect in the future, we don't expect. The same with volcanic eruptions. We don't need to worry about what's happening in the future. Those effects, they may occur, but we don't expect them to be as large as what will happen if we keep changing the concentrations of carbon dioxide. And so what do we use for the concentrations for carbon dioxide? We don't know what they will be, but what the scientists or the climate science world has done is to postulate that the greenhouse gas concentrations will change according to how the global economy addresses the emissions or the burning of fossil fuels and greenhouse gas emissions. And what they do is they assume one type of emission scenario, for example, an unchecked or a do-nothing type of approach, in which case the greenhouse gas concentrations increase forever and a day, or they look at the options of trying to reduce greenhouse gas concentrations by trying to reduce the emissions or the burning of fossil fuels by, for example, aiming for net zero emissions by 2030 or 2050. And by looking at a range of these scenarios, and the scenarios are all given by are indexed with numbers here, SSP 119, RCP 2.6, etc. They're the low greenhouse gas concentration scenarios up to the more unhealthy ones in red. And they do the simulations with the climate models, and they look at what the effect is of each of these postulated greenhouse gas concentration pathways is. And that's what this time series reflects. Again, it's a plot of global annual temperatures from the models, from lots of models, many experiments, looking at both the past, in this case from 1950 up till about 2015, for which we've already seen the models do a pretty good job at reproducing the observed temperatures, and then launching ahead in time through the remainder of the century right through to 2100. And you can see the different trajectories that the simulated global average temperatures take, depending on the emissions scenario that's been assumed. And as I say, the top trace, the one that's heading up towards maybe plus 5 degrees, between 4 and 5 degrees, corresponds to relatively unchecked emissions by the global economies. Next one down involves slightly reduced emissions, and so on, right down to the bottom two, which reflect what could happen if we make an effort to aim at zero net emissions by around about 2050 or earlier. And that the bottom two traces are the ones that governments would like to aim for, because they've decided that assuming the models are right, that a warming of more than 2 degrees is unacceptable. They don't want the globe to deal with the impacts of global warming of plus 2 degrees or more. So the bottom two trajectories are essentially the reason why governments have agreed to at least aim for zero net emissions at some stage, because even though the warming will continue and it's not going to start cooling, it's highly unlikely to begin cooling, we limit the temperature increase to below 2 degrees. That's the basis of why governments have adopted those limits on global emissions. Now, part of the reasoning, or part of the reasons why governments and scientists and everyone would like to limit things to 1.5 ideally, to maybe definitely not 4, is indicated by these results from the climate models. And these show the patterns of global warming if the world warmed by, starting from the left, 1.5 degrees, in the middle 2 degrees, or at worst warmed by 4 degrees. There are no dates on these. It's just simply the results of the models when global average temperatures in the model world reach these thresholds. And the general picture is one of very much warmer temperatures. If we look to the more extreme case of 4 degrees, you can see very high temperatures in the polar regions, especially up in the Arctic regions, particularly warm over inland areas, less so over the oceans. Those sorts of temperature changes are deemed relatively unacceptable or very difficult to adapt to. We do the same for rainfall. We can look at the output from the model results, and insofar as we can believe the model results for rainfall, given that it is a very difficult thing to simulate, again, we can see what happens at 1.5, 2 and 4 degrees. The patterns there are much more complex. The darker greens indicate where it's getting wetter according to the models. Again, the strong message is for increases in the Arctic and polar regions and the equatorial Pacific. Over Australia, the signal's not strong. This brings us to another issue, that even if in a warmer world we don't see a change in average rainfall, it's quite possible that we can see a change in the intensity of rainfall. For example, we could have more but less intense events, or fewer, more intense events. And the evidence and the thinking on what to expect tends to favour the second of those outcomes. And I think maybe the events over the past few weeks are not inconsistent with that, that thinking, that in a warmer world, we're more likely to see fewer or maybe the same number of rainfall events, but they will become more intense. If we look at the daily rainfall record from a place within your region known as Carroll, bracket the ranch, this is the daily rainfall record for 8 years, 1996 to 2008. And you can see here that on occasions, daily rainfall amounts have exceeded, well, the maximum there is 100 millimetres back in 2004, 80 millimetres sometime in 1997, and certainly more than 50 millimetres, which is a couple of inches in a day on quite a number of occasions over that period. And the interesting thing here is what would happen if that same sequence of events occurred in the future, and but the world was warmer and the atmosphere held more moisture? Well, scientists have looked at how much wetter, how much more intensification would take place under different amounts of warming. And I'm aware of the time. I'll just point out that under a 4-degree warming, the estimates is that rainfall events could be 30% higher. And if we go back and look at the graph from the Carroll, the ranch, the little red additions to the daily rainfall bars indicate what a 30% increase in intensity would mean. The 100 millimetres in a day would be going up to 130. The 80 would go over 100. And if you did that to all the daily rainfall amounts on this chart, you would see a strong shift towards the more intense events. The question is how serious those events are. Can you adapt to changes such as those? And that's probably a question that can be answered in ensuing discussions that follow this particular presentation. Now, I'm getting towards the end of the talk. I want to leave some room for questions, but you can look up the projections for New South Wales, and nothing I'd say is particularly new other than we can expect it to get hotter, annual temperatures to increase, the number of hot days will increase, and the only way to avoid some of those increases is to restrict global greenhouse gas emissions and try to keep the ongoing warming to between what, in this case, 0.7 to 1.4. There are more projections and projected impacts in in the official information that you can dial up. For example, the climate of Sydney is projected to be more like the current climate of Grafton. That of Broken Hill may be more like the current climate of White Cliffs. Longer fire seasons, increases in sea level. The projections for rainfall are that definite. There's some evidence that summer rainfall might increase and winter rainfall might decrease. Extreme rainfall events are projected to become more intense. And as a consequence of some of those changes, increase in snow melt will result in a decline in snow in the Alps. Now, you can dial up more specific information for your region, and there are sites available. The Climate Change in Australia publication that is put out refers specifically to the Central Slopes, and there are interactive options for people to look and dial up some of this information. For example, changes in temperature. You can see here the projections for particular regions such as the Northwest Slopes. High confidence that the warming will continue, both the mean, the max and minimums. They're highly confident the frequency and duration of hot spells will continue. Nighttime temperatures will increase, frequency of frost days will decline, and they're very confident about those projections. Decreases in winter rainfall are projected to become evident by 2090. They seem to be confident that that might be the case for your region. Some decreases are projected for spring, but the confidence is only medium. Potential evapotranspiration is a high confidence that will increase, leading to soil moisture decreases predominantly in winter and spring. Medium confidence in that. Harsher fire weather, highly confident of that. And a lot of these impacts are dependent on the rainfall predictions. As I've said, the rainfall predictions aren't as definite as the temperature projections. There are other impacts outside your region, but for key areas such as the Great Barrier Reef, they're at particular risk if temperatures increase by 1.5 degrees. There are impacts on the alpine communities, and so with increased temperatures and possibly a slight decrease in rainfall, the possibility exists that the conditions for snowing and the ski industry might deteriorate. The summary is there. Again, it more or less reiterates to some of the things I've said. The bottom point here is that some systems may go beyond management limits or their ability to cope if global warming exceeds 1.5 degrees. And that's the reason why zero net emissions by 2050 or even earlier is so important. And some recent slides that I put in just yesterday, but which I've labelled under stop press. Brisbane has just had its wettest 3-day period on record, and somebody is quoted down below. I grew up in Brisbane and the 1974 floods were rare. Now we have had 2011, 2013, 2017 and 2022. This sort of unfolding of changes to climate and increased impacts will feed into our knowledge base and maybe firm up our confidence in the projections going forward. Despite all that rainfall that we've received up till the end of February, if you look at the longer term, say the 4 years up ending at February, the trends in rainfall again is very difficult to trends in rainfall, and simulating rainfall is a difficult task. this pattern doesn't resemble anything like what we've experienced. Just goes to show you, again, how variable rainfall is. It can be very wet one year, very dry the next year, but the long-term pattern is not is often not consistent. And lastly, we've just had a release of the Climate Change 2022 by the IPCC. I haven't had a chance to go into it in detail, but I think the important message from this particular report is that dealing with climate change involves two options. Mitigation, that is trying to reduce greenhouse gas emissions and reduce CO2 concentrations, and or adaptation, that is accepting that changes will take place and you need to prepare. But the message from this report, I believe, is that the window for adaptation is rapidly narrowing. And if people don't get a move on, they'll run out of time to prepare for the changes which may be inevitable. So I would like to end the talk there and thank you for listening.